Today we're going to be covering the halogenoalkanes, which are also known as the alkyl halides, and we're going to be looking at their different reactions and the different types of mechanisms associated with these reactions. So just to recap from the last class, primary is where you have one or no alkyl groups attached to the carbon that is attached to your halogen. Secondary has two alkyl groups that are attached to your carbon that's attached to your halogen. Lastly, you have your tertiary halogenoalkanes, and this is where you have 1, 2, 3 alkyl groups or your methyl group attached to the carbon that is attached to your halogen. In terms of stability of your halogenoalkane, your tertiary halogenoalkanes are more stable than your primary. This has to do with your alkyl groups, methyl groups that are attached to the carbon that is attached to your halogen. These alkyl groups affect stability because they're also considered your electron donating group. These methyl groups here on your tertiary increases the electron density in the molecule, meaning that they're pushing negatively charged electrons towards your electron poor positively charged carbon and forms a stable carbocation. If you remember your carbocations from a previous topic, your tertiary carbocations are more stable than your primary and secondary carbocations. Bromine is more electronegative and is pulling the electron density within that carbon to bromine bond towards itself, giving your carbon that partially positive charge. Once the bond between your carbon and your bromine is broken, in order to stabilize that positive charge on your carbon, because the carbon is not electron deficient, so in order to stabilize it, your methyl groups or electron donating groups push electron density towards your electron deficient carbon and stabilizes the formation of a tertiary carbocation. Right? In comparison, your primary halogenoalkanes would have one or no alkyl groups attached, and these would not be able to stabilize the carbocation that is formed. In addition, your primary halogenoalkanes are going to be forming your primary carbocation intermediates, and these are the least stable of your carbocations. Right? So your secondary halogenoalkanes can undergo both SN1 and SN2 nucleophilic substitution mechanism. This is influenced by your solvent, your nucleophile concentrations, and steric hindrance. In the case of your tertiary, these undergo your SN1 substitution. Primary undergoes your SN2. Now, in terms of what your SN1 and your SN2 means, your S stands for substitution because we are replacing your halogen with nucleophile group. It could be your OH, your water molecule. But again, your nucleophiles are negatively charged or partially negative charge. They have lone pairs of electrons or just electrons available to donate to an electron deficient atom. S stands for substitution. You're substituting your halogen by your nucleophile. N stands for nucleophilic because we're undergoing nucleophilic substitution. The number, whether it's 1 or 2, tells us amount of species that are involved in forming your intermediate. It also tells us the amount of reagents that are involved in the rate determining step. So in your SN1 for your tertiary halogenoalkanes, you have one species involved in forming the intermediates, and that same species affects your rate of reaction, and that would be your halogenoalkane. So we're looking at your tertiary halogenoalkanes and we're looking at your SN1 mechanism. So again, you're going to have those 3 methyl groups that are electron donating and are pushing electron density onto your carbon to form that stable tertiary carbocation. This alkyl group causes the electrons of your carbon to your bromine in this case, or your carbon to your halogen bond, to be pushed fully onto your bromine. So the 2 electrons here are now being pushed onto your bromine. This causes your carbon to bromine or your carbon to halogen bond to break, undergoing heterolytic fission, and form your stable carbocation that is here. Because this carbocation is now carrying a positive charge, it is going to attract your negatively charged nucleophile. And in this example, your nucleophile is your hydroxy ion. And this is going to be your substituted product here, which in this example is an alcohol or a tertiary alcohol. Next is your SN2 mechanism. Your primary are highly reactive because they do not form stable carbocations. They are instead going to undergo an SN2 mechanism. So under SN2 mechanism, you have two species involved in forming the intermediates in the rate determinant step. So for your SN2 mechanism, the rate of reaction depends on both your halogenoalkane and your nucleophile. Because your primary halogenoalkanes do not have a lot of bulky groups, or they don't have more than one bulky alkyl group attached to them, the carbon is essentially not crowded or not blocked out by these bulky groups. So your primary halogenoalkanes are said to have low steric hindrance. That means that your nucleophile can attack the carbon from the backside where it has the least amount of steric hindrance. So it's easier for this nucleophile here to attack your carbon from this position. This backside position is further away from your halogen. Your nucleophile will attack from this position or from this backside orientation due to low steric hindrance on this side, and it's also due to less repulsion because it's not coming towards your halogen that is negatively charged. So there would be no repulsion between your nucleophile and your halogen if your nucleophile attacks from that backside. Your halogen is partially negative, so your electrons are being pulled towards your halogen, weakening your carbon to halogen or your carbon to bromine bond. The nucleophile, which is your hydroxide ion, approaches the partially positive carbon atom from the back, least hindrance, and it forms a bond between itself and the carbon atom. So in your intermediate, you have a 5-coordinate species, right? So this 5-coordinate species here lets you know that a bond is being formed between your carbon and your nucleophile, while a bond is being broken between your carbon and your bromine. So this is your intermediate also, or your transition state, giving you your final product, which is also an alcohol. This is another image of your SN2 mechanism that doesn't quite depict the hindrance point, but the same thing still applies. Hydrolysis reaction, or the production of your alcohols from your halogenoalkanes, actually produce the fastest utilizing your aqueous sodium hydroxide. This is going to give you your hydroxide ions as your nucleophile. This reaction actually slows down if you utilize your water molecules. So if you were to compare your hydroxide ions and your water molecule, you would notice that your hydroxide ions are carrying a more negative charge than your water, making it a better nucleophile, and why the reaction occurs the fastest with your sodium hydroxide. Reaction with your concentrated ammonia, this is going to produce your amines, you produce your nitriles from your cyanides, and elimination reactions. So in regards to your rate of hydrolysis, this is also related to your bond strength. So this is looking at the bond between your carbon and the respective halogen. So as you should remember from your unit 1, your bond strength relates to your bond length. The longer the bond, the weaker the bond, the less energy required to break that bond. The shorter your bond, the stronger your bond, and the more energy required to break that bond. So your rate of hydrolysis increases from your fluorine to your iodine because your iodine is a larger atom. Therefore, it has a lot more shells and it's gonna have a longer bond between your carbon and itself. And because the bond is longer, there's less attraction between your iodine and carbon, it is easier to break that bond, hence the rate of hydrolysis is occurring faster because it takes less energy to break that bond. So here again, you just have the different equations associated with your different types of reaction. As mentioned, your halogenoalkanes can undergo your elimination reaction. It is important to note, if you use your ethanolic sodium hydroxide instead of your aqueous sodium hydroxide, you are actually going to undergo an elimination reaction if you're dealing with your sodium hydroxide in ethanol. This is actually going to produce your alkene, water, and your sodium bromide. In terms of producing your nitriles, you're looking at the addition of your cyanide, and this is going to produce a nitrile. You have a substitution with your ammonia to produce your necessary amines. This reaction occurs once your ammonia is in excess, the solution is being heated in ethanol and under pressure. So lastly, we have a few questions that you're going to practice on your own, and we're going to look at them on Wednesday. So for your different questions, you're going to be writing an equation and giving the mechanisms for the first three reactions. It is important for you to determine whether or not your halogenoalkane in that question is primary, secondary, or tertiary. And then you're also going to be looking at your reagents to determine what nucleophile is being used. Once you know what nucleophile is being used, you know the product that you're supposed to end up with. In terms of your question 2, you're looking at the bond length in association with the bond strength. Right. So which one has the weakest bond, hence which one is going to react the fastest. And in the last question, you've been asked to do a mechanism for a particular type of your halogenoalkanes. So similar to sodium hydroxide, but your potassium hydroxide, you're going to have a different reaction depending on the conditions, whether it's aqueous or it is reacting with ethanol.